So the next presenter is Agnes Mazot from GNS Science from New Zealand. So for Agnes, it's early morning, should we say?
In the middle of the night.
In the middle, it's almost morning.
Yeah, 3 in the morning, 3:30. Okay, so kia ora everyone. Welcome to Aotearoa, New Zealand. And I will share my presentation. Just a second. Okay, can you see that?
Yes.
Okay. So today I will talk about volcanic lakes again, continuing with Dimitri, and talk especially about carbon dioxide degassing. And so you can ask the question, why studying carbon dioxide and why the emission and why volcanic lakes? So yeah, so we will try to answer the question today. And just to remind you, Dimitri really explained really well about volcanic lakes and gas emission from there. But just a reminder that, yeah, of course, magma contains dissolved gas deep in the system, 10 kilometers or deeper. And the main volcanic gas or magmatic gas are water, of course, for 90% of the case. And CO2, NO2, hydrogen sulfide, H2S, HCl, and HF. And they are 99% of dissolved gases in magma. And as Dimitri was saying, each of these gases has different solubility in magma. And when you've got magma rising, you've got depressurization, and you've got different solubility from the gases, and you've got exsolution of gases when the magma rises. And there is some changes in chemical composition of the gas. And so when you measure the composition at the surface of the dissolved gases and their output rates, you can follow the evolution of a volcanic system and also monitoring them. And volcanic lakes in particular are really good because they trap gases, and they are a good representation of what's going on below. On the left, you can see the graph with the magma at depth. And you've got the lake at the surface that usually it's a mix of water and meteoric water and also magmatic gases. And in between the magma and the surface, you've got an hydrothermal system that is a mix of magmatic gases, meteoric water, with the heat of the magma and everything. So it's a really complex environment. And depending on the temperature, you can have more gases or more water, more fluids. So it's a really complicated hydrothermal system. And when you've got a lake, the good thing with the volcanic lakes, it's easier to sample in a way because it's a lake. So you've got all the gases trapped in there and you can sample them, and it represents your volcanic system in a way. And also measuring the gas emission is really important. And depending of lake's pH, as Dimitri was saying, that you can have with acidic water, you can have the CO2 is going straight through the lake. And also the SO2 emission can also give us some information. And that's why it's important to monitor this composition and the change in output rate. So here, show you two different graphs. On the left one, you've got the CO2 SO2 ratio with the pressure that is related to the depth. And for example, 50 megapascal, it's representing 2 kilometers deep, more or less. And so you can see on the left that depending on the CO2 composition in the melt, in the magma, you can have different ratios of CO2 and SO2. And the ratio CO2 SO2 can help us to understand deeper processes. And on the right, you can see also the same, the depth versus the volatiles, the solubility of the gases, the main gases in the melt. And you can see that you've got the water, you've got SO2, and you've got CO2. And you can see that the CO2 doesn't like to stay in the melt when the magma rises. It starts to go out to exhaust from the magma at quite deep levels, like more than 10 kilometers. And usually when the magma is going shallower, maybe 4 kilometers, the CO2 is almost degassed. And the SO2 is completely different because the SO2 stays in the melt until the shallower levels, say 2 kilometers, and start to exsolve at 2 kilometers deep. So you can see more, of course, SO2 is really important and it's more for shallower processes, but you can have also some more hydrothermal interaction. So it also helps to understand better the processes, what's going on below the volcanic system. And the water, of course, it's the last one to exhaust from the magma. And so why I show you this, it's because CO2 fluxes is really important to see deeper processes. So and also to help about early warning system of volcanic eruption. And it's what I want to show you with examples of, for example, Kelowd volcano, measuring CO2 flux help a lot. And how do we measure this CO2 flux from volcanic lakes? Because, how can we measure? We are not sampling some points in the lake. We are measuring the gas emission that just at the surface of lakes. And this method is called floating accumulation chamber method. It's coming from the measurements we usually do over soil or ground, volcanic system, geothermal system, and it's coming from Giovanni Chiodini, who started to use this kind of system to measure the CO2 flux from the ground. And we modify this system to make measurements of a lake, just using a floating chamber. So how does it work? You've got on the left, you've got a system, you've got like a chamber, like a pot, reverse pot, and it's connected to a spectrometer that measures the CO2 concentration. And this CO2 that is coming from the ground on one of the picture from the lake, it's going through the pipes and go to the spectrometer where it's measured the CO2 concentration. And after this CO2 comes back into the chamber or pot and it accumulates. And because you've got always CO2 coming from the ground and going into spectrometer, you've got an accumulation of the CO2. And with time, you've got an increase in CO2 with time. And using the slope of the time versus concentration, you've got a flux, easy peasy. And it's what you have on the hand-sized computer here. You have an increase of CO2 concentration with time. And using the air temperature, the air pressure, you've got a CO2 flux usually we use units mole per square meter per day or gram per square meter per day, depending of the different researcher or users. And so we use this technique on CO2 on lakes, and it works really well. It's amazing. So you've got different type of measurement style. You can use a floating boat and rowing hard. You can use also pedalos, like Lake Monticchio, Lago Monticchio in Italy. You can also go on El Chichon and really hot day and also row on lake, or you can really be fancy and more luxury using a boat on New Zealand and also measuring the CO2 flux using different kind of boats or system. I haven't used a kayak yet, but I think it's on my list next time, using kayak. So, well, how do we measure? So how do we measure to be sure we represent all the lake and all the important feature of the lake? So you've got different example of lake. So for example, on the top left, you have the Lake Kelut in Indonesia. So you've got the lake shore in black, and you've got blue the lake. And the white dots are the points of measurement. It was around 25 meters. And here you can see that it's really irregular. So it's, this is strange, it's too regular to be true. But no, it was true because we used rope at this time. And because the lake is not really big, it's 200 meters of width. So it's not big at all. So we could use rope. It takes a while, but we did it. And that's why you've got so really good measurement space in this one. On the top right, it's a little bit more random because this Lake Rotomahana in New Zealand, you can, on the left part of the lake, there are more points because there are more activity of features there, more bubbling areas, more hot water. On the right, you can see the space, it's less because there is much less activity there. So we didn't need to measure every 100 meters. So we use a space of 200 meters for this lake. And so what we do, we put the chamber on the water, we measure the GPS, we finish the measurements, usually takes around 3 minutes, 2 to 3 minutes. And after the end, we measure the GPS at the end, and we do a compilation of the GPS in between, and we use this site as a point of measurement. And the lake Rotomahana is much bigger, and so we couldn't use rope because we couldn't do that. It's impossible. We've got another on the bottom left. You've got another lake, El Chichon, Mexico, as Dimitri was talking, and so it's also more or less random because you can see the points there. But actually, we cover all the lakes, so it was the most important thing here. And Lake Ruapehu on New Zealand, so it's not a big lake either, but it's quite deep, 100 meters deep for the deepest the deepest bottom lake. And so here you can see that the points are really a few points, and I didn't cover all the lake because we didn't have time to finish, and we had only a few hours to do that, and so it was really hard to make all the measurements, but at least we've got a few points, and it helped to understand the processes from Lake Ruapehu. And so how the CO2 is going through the lakes, it depends on the pH, of course, as Dimitri said. If you've got pH really low, under 3, usually the CO2 is going through the lake easily. It doesn't really stay in the lake. There is no reaction with the water. But when you've got lakes like Lake Rotomahana, New Zealand, you have much more reaction in the CO2 with the water. And so you've got 2 different processes. The first one, as obvious it is, you've got the bubble, so you've got CO2 going through the lake via bubbles, and it doesn't, of course, it dissolved And sometimes when you've got really strong flow of bubbling, the CO2 is going to the surface without any reaction, or is dissolved, but is really going fast. And so you still have bubbles at the surface. But the other process is CO2 diffusion at the water-air interface. On the right, here you can see that you've got the water, you've got the air, atmosphere, and the CO2. So there is like a diffusion layer, really small layer, less than millimeter, would say. So you've got the CO2 with a certain concentration in the lake, and you've got a CO2 that is usually 300, now it's 400 ppm in the air. And so if you've got, of course, more CO2 in the water, that's what's going on Lake Watamahana and different lakes in New Zealand and Chichen, for example. You can have some CO2 going from the water to the air because of diffusion to the air, because there are more in the water than the air. And so they are the two main processes that's going on volcanic lakes and how the CO2 is behaving. So after we made the CO2 flux measurement at surface of the lake, we want to process the data first to differentiate between the two processes, and second, also to map, to see where are the most important CO2 degassing and the general output of the CO2. And we have two different kinds of processing. The first one, we call this a statistical graphical approach, that from Sinclair. And it's a way to differentiate populations or processes for a case. And the second one, it's the sequential Gaussian simulation. Sounds really complicated word. It's a geostatistical program that interpolates CO2 flux and help us to make a map and show CO2 flux anomalies on a map. So the first processing is about graphical statistical approach. So you have on the graph, on the x-axis, you have the log of the flux of CO2, the logarithmic CO2 flux. And on the left is the cumulated probability of the flux in percentage. So in this graph, you have in black, the dots are your measurement points. And you can see from -1 to 4, you have your flux. And you have an inflection point in the middle. And this, it's your threshold that gives you the percentage of what is coming, for our case, from the bubbling and what is coming from the diffusion. And using this method of processing, you can differentiate these two populations and have these two populations with different statistical, like the mean, the minimum, the maximum, the range. And so it's what we want to do here. And doing that, you've got on the right with the blue square and the line, you have the population with the bubbling. And so and this population's got a mean, it's got a range, and you've got standard deviation. And also on the left, you've got the other population with the mean and the standard deviation the same, and coming from the diffusion for our case. And doing that, you can estimate what is coming from the bubbles and what is coming from the diffusion. So it's quite a good way to see what's going on volcanic lakes. So the next processing is for mapping and using the sequential Gaussian simulation. So you've got on the top left the Lake Keluk in Indonesia, and so what the measurement we've made in the lake. So you've got your measurement points with certain values, and you have on the first lower graph the flux CO2 flux with a frequency. So you've got an histogram. On the top, you've got a spatial distribution of the value. So you've got two different kinds of representation from the original data. You've got the histogram and the spatial variation of the value between pairs of data. Using this, the sequential Gaussian simulation, what does it do? It uses this data and the original data to make a lot of different simulations, interpolation of what can be the result of a map at the end. And you put all these simulations together and you end in the final representation of an average of all realistic representation of your mapping. But you can say, yeah, but what is the point? You can use Kriging, you know, the normal Kriging interpolation program or simulation. You don't need to do all these complicated things to arrive at the same result. No. Why I use this, or why we use this researcher? Here you can see first on the left, you can see on the top one, it's from the Kriging, using the normal Kriging with that. It's just one simulation first. And on the bottom one, it's a stochastic simulation. And this one, you can see that on the bottom one, you can see an anomaly that using the Kriging doesn't show here. So it's quite important to use this stochastic simulation because the Kriging, there is no error estimation first, and it's smoothing the estimated values. So you can't see anomalies that you can see from the stochastic simulation or sequential Gaussian simulation. And also this method reproduce the statistical and spatial characteristics of the original values. And you have an evaluation of uncertainties because you've got 100 simulation, 500 simulation, and so you can estimate an error of that. So it's really good to understand that. Now I will present some example of study of CO2 degassing from volcanic lakes. So one Kelud experience to show the temporal evolution. Mexico for highlighting structure, and in New Zealand, Rotomahana showing pathways to deep magma, and Ruapehu, an active volcanic system in New Zealand. So first, the Kelud experience. So Kelud is located in Indonesia, in the main one of the island, and in Java, and it's located on the right, on the east side of Java. So Kelud volcano, as you know, it's got frequent magmatic eruptions, and the last one was in 2014 with a Plinian eruption. It was and destroyed a dome that was there since 2007. And it's got the volcanic lakes, of course. And before a long time ago, the volume was 40 millions of cubic meters. That was a lot. And then they made some tunnels and tried to decrease the volume, and they went in 2 million cubic meter, because when Kelud volcano is erupting, it's got devastating lahars following that. So that's why it was really important to decrease the volume of the lake, and so to reduce the hazard. And since then, we had much less hazard, but still, Kelud is really densely populated around, and really, really, really dangerous, even if because we have a lake. So why we measure CO2 flux from this lake? Because, as you can see on the bathymeter on the right here, that you have a lot of bubbles, and it's everywhere in the lake. And the pH is around 6, so you've got bubbles, but you can also have some diffusion in there. And here it's the result of the CO2 flux measurement we made. So we started in 2001, was the first time we made CO2 flux measurement on the surface of the lake. We've got 100 tons per day. And it was so after there was an increase in temperature, lake temperature there. In 2006, we had 35 tons per day. And in July, August 2007, what's going on? It's strange. We've got 330 tons per day. Maybe there is something wrong with the instrument, so it was really strange. And actually, it was real. And a few months later, you can see here, there was a dome appearing in the middle of the lake. So it was a good way to see that CO2 flux is really a good parameter for early warning system of volcanic eruption. So here, I've done the graphical statistical approach to differentiate between the two populations here. And so you can see from the bubbles, you've got, the values here, 900, 950 grams per square meter per day. That's quite a lot for a lake. And from the diffusion, you've got also a few, CO2 flux of 130 to 150 grams per square meter per day. So it's quite high too. And so using this differentiation, you can estimate what is coming from the bubbles and what is coming from the diffusion. And here it's just to show the CO2 flux mapping, CO2 flux mapping from using the sequential Gaussian simulation. And you can see from 2002, 2003, 2004, you can see the changes in behavior from the lake every year. And in 2005, oh my God, it was so noisy that the simulation was getting really, because it was so low. It was not good. And here, from 2006 that we measure on top, you can see a lot of blue and it's really low. And suddenly in 2007, you can see on the scale that 7,000 grams per square meter per day. Yes, suddenly you've got like a really high increase in CO2 flux emission, and it was in July, August 2007. And in September 2007, we started to have some seismic records of seismicity on the volcano, and it was September. And in November, we started to see the dome appearing in the lake. So here, just to show you that how the CO2 was showing really quickly because the magma was rising from deep, and the CO2 was the first to exert. And it's when we saw in 2007, in July, that the CO2 flux was really high at this time. So you can see on this graph that you've got the timeline and CO2 flux on the left and lake temperature on the right. And you can see that the CO2 flux was higher before the lake temperature increased. And so as said Dimitri, the water is taking time to react, and the lake temperature is taking time to react because it takes a longer time for the water, the fluids coming from deep to react in the hydrothermal system than the CO2. The CO2 is going straight to the surface. So that's why CO2 is really important for early warning system of volcanic eruption. Now I will talk about El Chichen experience and more about highlighting structure in there. So El Chichen is in Mexico, and the last magmatic eruption was in 1982. And we had also a lot more explosive events than the events of 1982. So here, just a baseline of the structure around El Chichen. You have on the right the volcano, and the crater lake is the small circle in there. And you've got all the structure around with some faults, and the main faults that are the San Juan fault. And you can see here what we have as geology and structure in the area. So we measured CO2 flux there, and using the floating accumulation chamber, as always. And we have some bubbles, of course. We've got a crater lake, 4 meter depth, really shallow, and quite cool or warm, 30 degrees, and acid, 2.3. So we've got CO2, yeah, like this of CO2, and not more, not really bicarbonate in there. And fumarole with temperature 98 degrees, and what Dimitri was explaining, the soap pool that is outside the lake. And we've got, of course, bubbling gases. That was really important for me. And we did some CO2 flux measurements in March 2007, in December 2007, and you can see that there are some we can see some anomalies in the area, some lower fluxes, higher fluxes, and some changes because the lake volume, of course, changes with time. And so you've got different area every time we go there. So you've got different result at the end, of course, because of the lake level that changes. And so this one, we did it in 2008. Oops, sorry. And so on the left, you have the CO2 flux measurements made only on the lake. And this year, there were CO2 flux measurements were made on the ground also. So it helped us to understand better the structure around the lake using measurements also in the ground. And you could see on the right, you've got some spotted high CO2 flux in there, and some areas where you have higher CO2 fluxes. And you can see that without the soil measurements, it was hard to say that there was some structure going on there. So on the right, you can see that there was some highlighting structure using the CO2 flux measurement. So it was really, really interesting to confirm the local faults and the regional faults that was in the area of Crater Lake, Chichen. And here it's a zoom out of so you've got the Crater Lake here in blue, and you've got the structure that I highlighted before. And here you can see the main structure also representing here. And it's confirmed that, yeah, it's the CO2 is using pathway and going through faults. So it was really interesting to highlight and to confirm this structure that was in there. Now we are going to New Zealand and studying two lakes, Lake Rotomahana and Lake Ruapehu. Just to have some background about New Zealand and the activity there. So you've got active volcanoes, of course, and it's coming from topovolcanic zone. On the right, you can see there is, like in red, it's the topovolcanic zone that is a rift that is opening. And you can see the rate 8 to 15 millimeter per year on average. It's quite active. And you've got volcanoes all the way through from White Island on the right up there. And when you go through, you've got Lake Rotomahana in the middle, and you've got Lake Taupo, where I live now. And you go down, and you've got Ruapehu at the end there, and the last one from the topovolcanic zone. And you've got all this caldera around there on the way also. So it's a lot of activity there, geothermal system. It's really, really, really complex. And if we zoom into Lake Rotomahana, so Lake Rotomahana is part of a volcanic center that is named Okatena Volcanic Center. And here on the left, you can see the border of the volcanic center. And it's not only one caldera, it's a few calderas in there. And it has been since 200,000 years ago. And Lake Rotomahana is this small thing at the end of the volcanic center. And it's coming from the Tarawera linear vent zone. On the right, there is a zoom in of Lake Rotomahana with Tarawera. That is, the last eruption was in 1886. And this Tarawera eruption in 1886 was a rift eruption with phreatic, phreatomagmatic, and magmatic eruption that occurred 10th of June in 1886 at night. And before the eruption, Lake Rotomahana was actually, there were two lakes. And on the right, you can see that the lake, there was the older Lake Rotomahana, and there were two terraces that was like wonderful, and a lot of visitors went there. And now, after the eruption, these terraces are underwater or destroyed, part of it, because of the eruption in 1886. So why measuring CO2 flux at this volcanic lake? Because you have fumaroles, you've got bubbling gas, and you've got geyser, and the volcanic lake Rotomahana has got a pH of around 7. So I did measurement there. We did around 400 measurements, and I used the graphical statistical approach to differentiate between diffusion and bubbles. And it was 95% of diffusion and only 5% of bubbles. But you can see that the transfer from bubbles, yeah, it's quite huge. It's 1,297 grams per square meter per day on average. It's quite huge. And you still have this diffusion that is the more or less background diffusion of CO2. And if we do the mapping using the stochastic simulation, you can see on the map here on that, of course, where the bubbling area is higher, you've got a lot of CO2 going through. And on the rest, but you still have all the lake, you still have CO2 flux measurement. And we estimated a total output of 500 tons per day. That is quite high for a volcanic lake that hasn't, where there was no eruption since 1886. So why we have so high CO2 flux, and it's not even active now. And on the contrary, we made also not only CO2 flux measurement, but we sample at different depths. We analyze for the isotope. We also analyze for helium isotope, carbon isotope. And we realized that the CO2 is coming from really deep, like 10 kilometers deep. And there is a pathway from this deep magma to the surface, and it's still going on. So we still have an active volcano in a way, because it's really still related to this deep magmatic system. And so in the future, we will still continue to measure and to monitor this volcanic lake. And the last volcano on volcanic lake I want to talk about, it's Ruapehu. Ruapehu, the last magmatic eruption was in 1995, 1996. And there was a phreatomagmatic eruption in 2007. And that triggered Laha, because there's snow in there. And so that's why we had, and there is a lake. So we, with the measurements I made in 2010, I estimated a flux of around 93 tons per day. And when we measure the CO2 emission from the plane, it's what we usually have as a measurement also of CO2 flux. And the mean of the CO2 flux on Wapihu is around 400 grams per square meter per day. And the area is not too high, but 200 square meter. But the depth, it's around 100 meters. And so here you can see on the right that the mapping, you can see there's some really high anomaly that is corresponding, that you said, Dimitri, that the north vent on the north part of the lake, that is the main vent that is quite active. And there is not so much in the central vent because, yeah, there is less, it depends also on when we measure the CO2 flux, because it's really changing. You've got a lot of upwelling going through. So if you measure the CO2 flux when there is an upwelling, you might have more CO2 flux going there. But at least we've got a background measurement there, so it's good. And so here I just wanted to show you comparison of CO2 flux comparing with the area of the lakes, volcanic or lakes, or also geothermal system, active volcanoes, any kind of volcano that we can compare with. And so you've got the x-axis with the area in square kilometer and the log flux, CO2 flux in megaton per year. And I just put here Rotomahana in there with the stars, and you can see how they're quite more or less related to more or less between them. And depending on the area, of course, you've got more or less CO2 emission from different kind of volcanoes or geothermal system. And on the left, you can see also the Kelud volcano with the different CO2 flux output, the CO2 output from 2001 to 2007. You can see also some evolution during time. And so all of these are how we measure and how we can use CO2 flux or CO2 emission for first monitoring or using as parameter for early warning system for volcanic eruption, or also for highlighting structure or understanding processes under volcanoes or volcanic lakes. And here, just because we are not, because of the technology and the evolution of measurement, and so we decided to think about how we can measure CO2 flux in a safe way, and using more continuous measurement, not measuring spot measurement and doing measurement, but just going with the boat, and CO2 flux is measured automatically, and so we don't need to use the processing simulation to have a map. And so this is the next generation working on at the moment, and you can see on the top right the same floating system, same floating chamber, but it's got a GPS, it's got everything, and it's measured in continuous, the CO2 flux measurement. And so we don't need to do anything, and we just have the flux, and that's it. So we just have the map. And how that is improving from what we are doing at the moment, so you've got on the top here the measurements we made using the new system, the continuous one, and comparing with the CO2 flux the accumulation chamber method we use now currently. And you can see on the left that first it's more precise because we measure it's continuous. And on the right, you can see the spot measurement. And when you do the mapping, it's like you've got a big blob of CO2 flux that is not there actually. So it's what we want to do in the future, and using this, also using a robot boat, and it's one of the thing we will do, and we want to use this technique using a robot boat that will go like a drone and doing the measurements alone. And for example, for Apehu, for future measurement, or for any volcanic lakes that are really hard to measure. For example, we have a lake, really hot lake, and really dangerous geothermal lake by Lake Rotomahana, and we can't have access, really, it's really dangerous. So using the robot boat, we will be able to do that and just let it go. It does the measurement, came back, we've got the data, and we're ready to monitor and do work without going there properly. And thank you for your attention.
Thanks, Agnes.
Any question?
Any questions? Agnes, one question from me.
Mm-hmm.
So because, for example, in Echitron, the
Yep.
area of the lake changed in time.
Yeah.
Is it important also, for example, I have, let's say, 100-meter diameter. In, let's say, 10 years, it shrank. So is it important, for example, if we do the flux on the lake, then go also around the lake on the shore? How relevant is it?
Yeah,
Because
it will be good.
degassing
Yeah.
also happens on the shore, which was previously a part of the lake.
Mm-hmm.
So how do you differentiate this? Where's the lake? Where's the shore?
Yes. Yeah. So usually what we do, we go around with a GPS and we measure the lake shore. And after so it's where we know where's the shore, the lake shore at this time. It's what we were doing with Dimitri also. Mm.
Okay. Any other questions? Another one from me. So when you have the flux measurement and what Dimitri showed us in the previous presentation, that vertical profile that they do you usually combine it, the two data, or you talk about separately, the flux measurement and the vertical profile?
No, usually I use also that because it's really important to not only make CO2 flux measurements, but also to sample the bubbles, to do depth profiles, to have a more complete data set, and so to have a better understanding of the processes that going on, for example, Rotomahana. And it's when you understand much better, you have the big picture of what's going on below the lake, and what's going on in the bigger picture in the volcanic system in there.
Thanks, Agnes. So if there are no questions for Agnes, thank you very much for staying up late for us.
No worries. Happy.
So thanks, Agnes, again, and see you guys next week.
Bye, Arthur.